Okay, welcome everybody. My name is Jeremy Wallace. I'm a senior solutions architect here at AWS, and I focus in robotics and the Robo Maker service. Really excited to have you here today. Today, we're going to be talking about running large-scale parallel simulations for regression testing as part of a CI/CD pipeline. So we'll start off with a quick primer on continuous integration, deployment, and delivery. We'll talk a little bit about ROS application testing and simulations. We'll discuss the AWS services that we will be using today. And then we're going to go deep into how to build a CI pipeline using AWS Robo Maker. And we're going to create in parallel simulations that are going to test for common scenarios that you'd want to test your robot applications for. Before we dive into continuous integration, deployment, and delivery, let's introduce the robot operating system. ROS is a flexible framework for writing robot software. It's a collection of tools, libraries, and conventions, and really has an entire ecosystem of packages and functionality that you can include out of the box to make your robot application development quicker. One of the key functionalities that we're going to be using today, and you'll see it later on in the instruction console demo, is the Colcon build tool. So Colcon enables you to easily build your ROS applications and all the packages within a workspace that you'd want to include within your ROS application. So let's say you had a robot arm and you wanted to have for the functionality to move that robot arm. There's a tool called Move It that you can package for Move It that you can just include within your application, and you get that functionality out of the box. So with ROS, you have all these packages, and with Colcon, you can easily build your ROS application using this tool and all the associated packages. And then with Colcon Bundle, you can take all the dependencies, including ROS itself, and package it up into a bundle that you can then easily deploy to simulation in RoboMaker, which is a service that we're going to be talking about at depth today, as well as package that bundle and deploy it to physical robots using our fleet management service. So that's a quick introduction. Now let's talk a little bit about continuous integration. So to start off, continuous integration is when developers merge their code on a regular basis. So usually what this means is that you'll have an integration branch in your version control system. Many folks out there use Git. And that integration branch is where all your developers will be continually bringing their code together to ensure that there's no downstream issues as you integrate what they're working on. Within your continuous integration pipeline, you'll also have automated build processes and tests that can run whenever an integration happens. And today, what we're going to be talking about is how to do that testing using simulation. Continuous delivery is creating ready-to-deploy artifacts that your team can deliver to your customers on a regular basis. This could be daily, weekly, it really depends on your business requirements. For ROS applications, when you're building robots, code for robots, this in the world of RoboMaker is going to be a bundle or a tarball that you can use with your RoboMaker fleet management. And we'll go into that in a little bit of detail in the upcoming slides. Continuous deployment is when every single change that goes into that continuous integration pipeline is then automatically deployed to a fleet of either test robots or production robots. This in robotics is a little bit more challenging to implement, as there's a whole bunch of conditions that you'd want to look for before you push new code out to robots. In a future webinar, we'll go into more detail about some patterns and how you can use AWS to successfully and safely achieve that outcome. So, why should you test your applications in simulation? Here's a couple key benefits when using AWS Robo Maker and simulation to test your applications. First, safety. Within simulation, it's possible to test edge cases and potentially dangerous situations that'd be very difficult to recreate with physical robots. Next is repeatability. So when you're running your test and simulation, you can recreate and rerun the exact scenarios that triggered unexpected behaviors. And so you can test for those conditions on a regular basis. And if you use a CI/CD pipeline, like we're going to show today, you could do this on a regular basis to ensure that your robots, when you add new code or new features, will be able to withstand these unexpected behaviors. Performance is another reason why simulation is a good approach to testing your applications. So in simulation, you can run your applications for elongated and extended periods of time. So you can see what happens to your robot applications over time to ensure that any new feature or development that you include doesn't end up degrading your either application performance or the performance of your physical robots. Coverage is another reason why you would want to test your applications in simulation. With simulation, you can parameterize the conditions that would exist in any given simulation run, which means you can run potentially hundreds of different scenarios to cover a whole bunch of different common scenarios that your robots would encounter. And finally, speed. The nice thing about simulation is you can actually speed up the wall clock time. So that means you can run potentially very long simulation runs in a fraction of the time by speeding up that clock time. So a common agile development practice for building software applications is behavior-driven development. So in robotics, what we're always looking for is to ensure that our customers are able to get the features and capabilities that they're looking for in their robots and the robot applications that we're building. So in this case, let's say our customers are wanting a robot that can autonomously navigate around multiple different store layouts, so it can pick up and deliver items to any location, even if we decide to redesign the stores. In this case, let's say the business stakeholders of your company are out there talking to customers or learning what they would want, and this is one of the requirements that they passed along. Those business stakeholders would work with the product management team to really define those scenarios and come up with an approach to how we can meet this customer requirement. When it comes to actually implementing this functionality within your applications, that's where behavior-driven development really enhances your capability to focus on that customer requirement. In this case, we have defined a scenario, and this scenario is user requests an object to be picked up, and we've defined our first scenario test case. For this test case, we've defined that given that Jane requires a robot to pick up an object and the store layout was redesigned, when she sends a pickup request to the robot, then the robot will successfully navigate to her location autonomously. So that's the behavior that the customers are expecting your application to perform given this scenario. So once we've defined that scenario, now we can actually include that scenario as part of our regular development and testing process through this CI/CD pipeline. And that's that iterative cycle that you see on the bottom right-hand corner of this slide. As product managers are working with their development teams to design this functionality, the developers are going to be implementing the functionality and then testing to see if it works. In this case, you could use simulation through an iterative process. You'd write your code feature, integrate it into a branch, test it amongst a set of scenarios that you defined in simulation, and see if your application successfully passes those tests. And then once it's ready, that tested, safe application code can then be deployed to customers to ensure that we're delighting them and meeting their requirements. So now let's talk about AWS Robo Maker, its core capabilities and how it can help you achieve this CI/CD pipeline. So first, RoboMaker has a cloud environment, cloud IDE, where you can build and develop your ROS applications. We have a set of cloud extensions, and so these are ready-to-go ROS packages to connect to a variety of different AWS services, which include things like Kinesis, which is our real-time stream processing service. It includes Recognition, which is our image recognition as an API service, and others. Next, we have simulation. This is the capability we're going to be focusing on most closely today. This is the ability to launch a simulation in the cloud through an API. So you have your ROS application code. All you need is a pointer to that code, and then a few minutes later, you can have a completed simulation run using tools like Gazebo, RViz, RQT. These are all common ROS application developer tools. And finally, we have a fleet management capability. This enables you to easily define your robot fleets and then deploy holistically across your fleet your new application code. It includes capabilities to do things like failure thresholds, conditions, so you can say only deploy to all the robots that are above 20% battery or higher, and those types of consistent and safe deployment patterns. So today we're going to really dig into that simulation piece. So the simulation service, with a simple API call, you can run ROS1 Melodic, Kinetic, or ROS2 Dashing applications within that managed AWS service. Like I mentioned, you have access to Gazebo, RViz, RQT to interact with that running application. The ROS bags that are generated within that application are written to Amazon S3 for future analysis and replay. And in addition to the physics-based Gazebo simulation, you can also use previously recorded ROS bags to test with sensor data from your production robots. And then finally, since this is a managed simulation service, you only have to pay for the number of minutes that your simulation runs. So this means one simulation unit, which is one vCPU and 2 gigabytes of memory, would cost you about 0.0067 cents per minute. So it's a really cost-effective approach if you just want to create a simulation, run it, and then have it shut down and terminate itself. So like we mentioned at the beginning, we're going to be testing for a whole bunch of different scenarios as part of this CI pipeline. To do that, we're going to use the RoboMaker simulation service capability to include environment variables as part of that API call that we're going to be leveraging. So on the left, you see the console. So if you were to go and create a new simulation application within AWS, this is where you define those environment variables. On the right, you can see the JSON objects that you would pass through to the API. One thing you'll notice is we have a few defined environment variables. These are the ones that you can use with our sample application today. One is simulation world, which will enable us to plug and play different Gazebo simulation worlds, which really fits that use case, that behavior-driven development use case that we got from our customers. In this case, they want to be able to simulate or they want to be able to run their robots in multiple store layouts. So in this case, we could have different simulation worlds for different store layouts. And then when we're testing as part of the CI workflow, test in a whole bunch of different store layouts to ensure that our robot application would function as expected across our customers' different stores. Secondly, we have a TurtleBot 3 model. So this is the type of robot we're using in this simulation, and you can plug and play with different configurations of that robot. Navigation success count. This is going to determine how many successful autonomous navigations we want to complete before calling the test a success. So maybe you want to try 10 or 20 if we want to ensure that the robot will run for long periods of time with multiple goals. And then finally, we've defined the region where this is going to run. And so these are the environment variables that we included within our application, which we can dig into now. But before we do that, I'll quickly introduce you to the API call that you could use to run batch simulations. In this case, this is the JSON definition that you'd send over when using this API call. Here's where you define the batch policy, so the time in seconds that your batch job's going to run, the max concurrency, the number of jobs you want to run at the same time, any tags you want to associate with this batch job. So since we're going to be launching a batch of simulations as part of our CI workflow, perhaps we want to include the commit from your version control system as a tag on this request. And then finally, we have create simulation job requests. This is just an array of all the job requests for each job you want to run. And that was in the previous slide, you saw that structure for the JSON. That's what you'd put into here. Okay, so let's dive into the code that we're going to be using today for our test case. So in the previous slide, I'd mentioned those environment variables that we're passing through in order to parameterize these scenarios that we're going to run. In this navigation test, we're taking in these environment variables, in this case, the navigation success count, so the number of successful goals to reach before we call this test a success, and then also a timeout value. So the first thing you need to do in the test case when using the unit test framework in Python is to define a setup function, which is going to set up your test. Next, we're going to define a check complete function. And so we're monitoring the state of this simulation. We're monitoring the robot as it's reaching its successful destinations. And if it gets to those destinations, at that point, we can check off as successfully reaching that navigation goal and then completing our test. And you can run this test with the unit test framework. It's just simply defining this run test method and then which components that you're going to run as part of this test. And so in this case, what we're going to define is the test navigation to run for this particular application. Now, a part of our navigation test application is going to be some utility code in order to interact with the underlying simulation job. So we're going to need to be able to do two things. One, which is set a tag. So in this case, we're going to self-tag the simulation job with the results of our test. So afterwards, we can do a describe of the simulation jobs that we ran and then see the status of the tests that were run in that simulation job. Did we successfully reach those navigation goals or not? Next is the cancel job method. This is going to enable you to self-terminate the simulation job while it's running. This is good because, as I mentioned, the RoboMaker simulation service is delivered per minute. So therefore, as soon as you cancel that job and it completes, you're no longer paying for the operating costs of that simulation job. So if your simulation is only 5 minutes long, you can cancel that simulation job once it's complete, and you only pay for the 5 minutes of simulation operation. So once we've defined this navigation test case, we're going to need to invoke it. So with ROS applications, you use a functionality called ROS Launch in order to invoke your ROS nodes as part of your ROS application. If you want to have any more, if you're new to ROS and you want to get a little bit more of a deeper dive on ROS, there's a lot of great information at ros.org. There's also this entire code base you can find online if you go on the bottom link here to AWS Robotics. It's in our sample application for robot monitoring and CloudWatch. So this ROS launch file that we're going to use is essentially just going to define these ROS parameters that we can pass through based off of our environment variables, as well as it's going to invoke our test node. The other important thing to look at here is this include file. So you'll notice that we are including the environment variable for the simulation world, which is going to enable us to send in custom parameterized worlds to meet our customer's requirement. Okay, so before we get into building our CI pipeline using this application code, let's dig into some of the AWS services that you should know before we get going. So first we have AWS Identity and Access Management. This is where you define the policies and permissions and different access controls for AWS resources. We're going to use this quite often throughout the solution, as each component is going to require access to different parts of our AWS environment. Next, we have Simple Storage Service. This is a highly scalable and performant, as well as durable place to store your files. It's an object store in the cloud where you can easily store things like our application bundles, our Lambda function bundles, everything that we need to access throughout our CI pipeline. For networking in the cloud, we have a capability called Amazon Virtual Private Cloud, or VPC. This is your ability to create your own custom-defined and controlled private virtual network within AWS. You can define subnets, you can define your own route tables to really control how resources, in this case, Elastic Compute Cloud virtual servers, are communicating within AWS. With RoboMaker simulation, you can define the VPC and subnets that you want your RoboMaker simulation job to run. This enables you to connect your simulation to other AWS services that are running within the cloud. So the other services that you're going to want to know today, first is AWS Lambda. That's a function as a service or event-driven compute. This is where you can just define a quick Python script and you can have it run based off of an event that happens either in the cloud or through external process. AWS CloudFormation is a common language for you to model and provision AWS and third-party application resources. So we're going to use this to package up our application alongside a capability for serverless applications. Serverless meaning you're using managed services within the cloud instead of having to provision those servers and the different services yourself. The AWS SAM and the SAM CLI tool enable you to create these applications using these managed AWS services. So the SAM CLI, it actually creates some CloudFormation for you, and that's going to be part of our first infrastructure creation step to get our step function state machine running, as well as, which is a core component that I'm going to introduce shortly, as well as some of the IAM, VPC, those various services that I introduced in the previous slide. It's going to enable us to configure those really easily. Okay, so the core services that we're going to be focusing on today, first is AWS Code Pipeline. So this is a continuous integration and delivery service that enables you to stitch together a set of stages and actions within those stages to deliver to both integrate code and have automated tests, as well as then deliver that code either to, it could be applications running in the cloud, it could also be applications running on robots. We're going to be using Code Build. Code Build is going to be one of those stages within our code pipeline, and Code Build is a managed build service where you can define the Docker image that you want to use as the base, and then run a set of commands to build your application code, and you only pay for the amount of time it takes to actually build your code. So we're going to be using the Docker image from OSRF as the basis of our build, and we're going to be running through the Colcon processes, Colcon being our tool to easily build and bundle ROS applications. So we'll be building that today. Finally, step functions. So step functions is a service that enables you to create state machines in the cloud. So in this case, we're going to use our state machine in the cloud to define the steps to launch our batch simulation jobs, as well as check and monitor and see what the status is of those jobs. And once they're complete, the final step in this step function state machine is going to be to collect the data and analyze it. And this is what the solution would look like once completed. So on the left, we have our development process for our ROS developers. They're developing either on their local machines or through the RoboMaker IDE. And then once they're ready to push their requests into the integration branch, once that merge completes, that's when we're going to kick off this code pipeline. We're going to run our first step, which is that code build, where we're going to build and bundle our code. And then we're going to kick off the simulations. And so the third and final step in our code integration pipeline is going to be to launch this step function state machine, launch a set of simulations for a set of different scenarios that we're going to be testing for, and then check on the status of them and then report back our findings. In a future webinar, we're going to dive a little bit more deeply into the part on the right, which is once we have code that is tested and ready to go, we'll be able to actually deploy that code to a set of test robots within a test fleet, physical robots, and then test it physically. And once we're ready to go, we can then take that blessed code bundle and push it out to a fleet of robots in production. But today we're going to focus on this part on the left. And this is what it'll look like once complete. This is the CI/CD pipeline that we have for today. The first step, we're going to clone our source. Second step, we're going to run that build in code build. And then the third step, we're going to simulate our application with multiple concurrent running simulations. All right, so diving in a little bit deeper into code build, as part of our application, we're going to need to include one of these code build specs. A build spec is essentially just a set of commands that you want to run as part of your build process. This you can actually include within your Git repository in the base folder of your Git repository, simple buildspec.yaml file, and code build will use that as its instruction set to run your builds. So in this build, we're essentially just doing some pre-commands to set up our build server, install Colcon, install some dependencies for Gazebo, as we're going to be building a simulation application. These are some install commands we have to run before we run our build. Code build runs its build processes in phases. And so you'll notice in the first section of this build spec file, in the first phase, we have install. These are those sets of install commands. In some of the next phases, we have the pre-build, where we're going to install some of the dependencies, and then the actual build, we're going to run the Colcon commands. The post-build, where we're going to run a bundle command to take the built ROS application code and then bundle it with all the dependencies into a tarball. Once that tarball is available, the last few commands in here, we're going to actually go ahead and upload it to S3. So today we're going to be using, as I was mentioning, AWS step functions to run multiple scenario-based simulations. To integrate easily with this step function state machine, we've written a JSON structure that makes it easy to decouple those scenarios from the actual parameters that you pass through to the request that runs when you run the simulation job API. So within the scenarios, here we have two scenarios defined: quick nav small house and multi-nav bookstore. So you'll notice one of them is running in the bookstore, the other one's running in a small house to meet our customer's requirement in that we need to be able to operate our robot in different layouts. And one of them is going to run 4 navigation goals. The other one's going to run a single navigation goal. So this shows you how you could really create all different variations of these environment variables to test in many different scenarios and improve that test coverage. Diving a little bit deeper into this step function state machine, here's what it looks like under the hood. First, we have a Lambda function that's going to process that JSON structure that you saw in the previous slide. It's going to create a set of requests, parameters for those single simulation job requests. And then it's going to go ahead and start the simulation job batch with that array of requests. So in this case, we only had defined 2 scenarios, so it's going to launch 2 simulation jobs, one in the bookstore, one in this small house world. And then once it's launched those simulation jobs, it'll move on to the next state in this state machine. The next state is to check on the status. So we're going to describe the simulation job batch, and once we get the results, we're going to go ahead and see if it's completed or if it's still running. If it's still running, we're going to put a wait 30 seconds, and then we're going to try again in 30 seconds. If it's complete, we're going to go ahead and move on to the next state, in this case, the summarize and process results state, where we can go through all the tags that were self-tagged on each one of those simulation jobs. If all the tests passed, we're going to send back a API request to the code pipeline to succeed this code integration job, and say that this code change has passed all the tests, and therefore can move on to the next stage in our delivery. If one or more tests failed, or if an error occurred during this process, then we're going to send a fail response to the code pipeline, and therefore fail this particular code integration. Okay, so now you got a high level of what the application architecture is we're going to build. Let's dig into the console and actually build it. So let's go ahead and get kicked off, and let's launch this thing. So the first place I'm going to go is into the AWS RoboMaker service from the Management Console landing page. What we've done for today, how we're going to build this is through the development environment within RoboMaker. Keep in mind you could use your own development environments that you have locally, as well as go ahead and create your own for today. All you'd have to do is press Create Environment in the top right-hand corner. So we'll go ahead and click on CI/CD Kinetic, which is the environment that I've created for our webinar today. Let this thing boot up. So to get kicked off, there's a couple things that I want to point out. First, we have our CloudWatch repository. So this is from the AWS Robotics GitHub repository that we've cloned. It has our test node that we're going to use for today's webinar. And it's what we're going to launch in simulation. Secondly, we have the ROS simulation launcher. And so this is going to be the back-end infrastructure that we will be using. In particular, this is the step function state machine with the associated Lambda functions to orchestrate the launching and monitoring of the batch jobs. So a couple Lambda functions to look at. Trigger step functions. This is what we're going to connect with our code pipeline. It's going to launch our step function state machine. Then within the state machine, we have a few Lambda functions. We have process and launch batch simulations. This is going to go ahead and take the JSON input. It's going to create a set of requests, and then it's going to go ahead and launch those batch requests. Next, we have check status. So once the simulations are launched, we're going to be checking it periodically to see the status. Once that is set to complete or failed, at that point we're going to move on to the sim summary, which is going to take a look at all the tags that are associated with those simulation jobs, and then determine did we pass or fail the tests that we had included within this set of batch simulation jobs as part of our CI pipeline. So these are the Lambda functions we're running. The step function state machine, as well as the configuration of these Lambda functions, are stored in this template.yaml file. So this is a serverless application model version of CloudFormation. So you can include other CloudFormation components in here like we've done in order to basically package up this backend infrastructure and deploy it. So for today, we're not going to really need to modify any of this. However, if you have unique requirements, feel free to go in and modify this. For now, we're just going to go ahead and launch it. So the first thing that we'll have to do here is create an S3 bucket that we can use to store some assets. So I'll start with that by using the AWS command line tool to go ahead and create a bucket. These bucket names have to be unique, So I will make this as unique as I can. I'm sure no one has that bucket name. And then we'll make sure this is in US West 2. Okay. Awesome. And so it looks like we've created our bucket that we can use to stage these assets. Okay, so the first thing that we'll have to do is build. And so the SAM CLI, let's just ensure that we have it installed. And if it's not installed, it won't be installed by default on the RoboMaker IDE, and as well on your local machines, if that's how you're doing this. So you'll need to go ahead and install the SAM CLI before we get started today. The first command we're going to run is the build command. So we'll start off with SAM build. In this case, we're going to use a container, and so this is a capability in SAM to use containers that are already pre-configured with the environment to build your serverless application. We're also going to specify a custom manifest file, so it will include the latest version of Bodo so we can leverage that batch simulation API. So we'll go ahead and run that command. So now what it's going to do is go ahead and run all of the build commands for each one of these Lambda functions. So we'll just wait for this to complete. Okay, so the next step is going to be to package the CloudFormation template with these built Lambda function bundles. So CloudFormation needs to have a pointer to the Lambda function zip files that we're going to use with the step function state machine and with this template. So the next step is to package that template, SAM package. We're going to set an output file, and we'll call that package.yaml. We'll also define the S3 bucket where we're going to stage these assets. And remember, we created this at the beginning of this exercise. Okay, let's go. All right, so you see it's uploading these Lambda packages. Perfect, and it's creating a template file. So now if we go ahead and open that, you'll notice this template file is slightly different than the other one. It has the pointers to all those Lambda functions in S3 if you want to inspect through this one. So this package.yaml is an actual template file that we can run in CloudFormation. And that's what we're going to do next. So we'll run a deploy. So we'll set the template file, home. Okay. And package, there it is. Okay, now we'll set the stack name. Now we'll name it something interesting. Let's do CI/CD with batch. S3 bucket. And again, this is that S3 bucket that we created. Now it's also important for this one because it needs the capability to create IAM resources. To have set capability named IAM. Okay, so let's go ahead and run this. Okay, so in this case, I've actually already run this once, and so it's just going to look for anything that needs to be changed. For you, when you first run it, it's going to go ahead and create all of the associated resources in the template. In this case, it's just going to update the Lambda functions themselves. So we'll go ahead and go yes. And then in a moment, we'll see that change. Okay, so now we've launched this CloudFormation template. So let's go and get the resource names of the items that were created. So if we go back to the AWS console and we open up CloudFormation, in here we can go and find our CloudFormation stack that was created. And under resources, what we can find are the IDs for all of the different resources that were created on our behalf as part of this CloudFormation template. So the ones that are going to be important to us today, we're going to want to know these subnets
And so you want to copy and paste these subnets, these subnet IDs. You're going to want to know the simulation role ARN. And so you can copy and paste this into a notepad file in your IDE. And you're going to want to know the robot application as well as the simulation application and the VPC. So if you copy this information into a place where you can reference it, then we're going to input it into some of our configuration documents. Next, we'll take a look at the CloudWatch sample application. There's a few components in here to take a look at. First, in the simulation workspace, you can find the test node that we've created for today's exercise. If we open up this folder, what you'll see are both the navigation test node with the code that I showed you earlier in the presentation, as well as the navigation test launch. So take a look at those components. Also in the base directory, there are 3 files to look at. First is the build spec. This is what we're going to be using with code build to run that set of build commands. This is important because you'll notice that before, when we went into our CloudFormation stack, it created a lot of those back-end infrastructure resources for you. So you're going to want to use the S3 bucket that was created by the CloudFormation stack. So we can go in to CloudFormation and go find our S3 bucket name. I'm sure it's in here. S3. There it is. Here's the bucket name. We'll copy that. And you're going to want to make sure to replace that in your build spec file. You can go ahead and press save. Secondly, you want to look in the scenarios.json document. This is what we introduced before, is the place where you can define those sets of environment variables for all of the different scenarios that you want to test your application in simulation. So here's where we can define those environment variables for the different scenarios. Here's where we can list the scenarios that we want to go ahead and create simulation jobs to test. And then below are the parameter set that's going to define the simulation job to run. So again, what you're going to want to do is go back to CloudFormation, go and copy all of the respective resource IDs into their locations in here. So there's a spot for an S3 bucket, there's a spot for an IAM role, there's a spot as well down here for your subnets and your security groups. So you're going to want to make sure to go and fill this out with those IDs that your CloudFormation template created on your behalf. The third file to take a look at is the RoboMaker settings.json file. So we're not going to be using this one today because we're doing our Colcon build and Colcon bundle processes, as well as running simulation through our CI/CD pipeline. However, if you were to do your development in this IDE, in the RoboMaker IDE, this is the file you'd use to configure the details about those simulation jobs. Okay, so now that we've explored this CloudWatch sample application, our next step will be to create our code pipeline. So if we go back to the AWS console and open up code pipeline, we can go ahead and get started. So the first thing you're going to want to do is press create pipeline to create a new pipeline. We can call it something interesting for today. Let's call it CI/CD webinar. And we'll go ahead and press next. The first thing it's going to do is create a new service role that this code pipeline can use to run various operations. So we'll have to define a source provider. These are the default supported source providers with code pipeline. Today we're going to be using GitHub. So we'll go ahead and press GitHub. We'll go ahead and connect to the GitHub. So this is going to connect to my set of repositories. And then in here, we'd want to define a branch. So in this case, I created a test suite branch that we can use, and we'll go ahead and press next. So normally that's where you'd want to define your integration branch. We'll select code build as the build provider, and we'll go ahead and create a new project that we can use with CodePipeline. Okay, so first we'll have to create a project name. Let's call this Kinetic Build Server for Webinar. This build. Okay, we'll want to select custom image, and under environment type, today we're going to be using Linux. You'll also notice that there's the opportunity to run ARM instances as well. So if you did have a ARM-based application for deploying to physical devices, you could have a build server that would also leverage ARM as the architecture. So we can continue on here. Instead of Amazon ECR, we'll select other registry. And let's go ahead and pick the ROS Kinetic Docker image in the docker.io. This is Docker Hub. So this image, like I mentioned, is supported by the Open Source Robotics Foundation. We can go ahead and create a new service role. For build spec, you'll see we have selected the configuration setting to use a build spec file. So that's that buildspec.yaml file that I showed you a little bit earlier, and we can leave the rest as default. Let's go ahead and press continue to CodePipeline. Okay, so now our code build project is created. Let's go ahead and press next. So we'll skip the deploy stage for now. Again, in a future webinar, we'll walk through how you can actually implement the CD component of this CI/CD pipeline and deploy to physical robots. So we'll go skip, and then press yes, and then we'll review what we've configured, and once we're ready, we'll go ahead and press create pipeline. All right, so the first thing it's going to do is an initial build. You'll notice we only have 2 steps in here. The third step in the CI pipeline here is going to be to kick off that batch set of simulation jobs. So let's go ahead and press edit, and then we'll add our stage. We'll call this stage simulate. And in the simulate stage, we can go ahead and add an action group. And we'll select the action provider AWS Lambda. We'll call this launch simulations. The input artifacts, you're going to want to set this to source artifact. And then for the function name, you'll see the 5 Lambda functions that were created and deployed using SAM. The one that we're going to select to trigger our step function state machine is this trigger step functions Lambda function. And then once we're done, we'll go ahead and press done. We'll review this, press done, and then up in the top right corner, press save. And we'll go ahead and press save. So let's go ahead and deploy a change with our new configuration settings. So the next thing we'll do is we'll kick off a new change to our code base with a couple small changes. So normally you'd have a feature branch that you're working on with the particular feature as a developer that you're implementing. In this case, we're just going to make some small changes to the build spec file. Remember, you had put in the S3 bucket from your CloudFormation outputs. And we'll add a commit message. We'll say update build spec with CloudFormation outputs. Cool. And then the next thing we'll do is we'll add our scenarios document and then update scenarios to match multiple layouts. Customer use case. Okay, so we'll go ahead and add that, and then finally we will do a push. So let's go back to code pipeline and see where we're at. Okay, so it looks like the build is in process. So in a few minutes after we've completed the build and bundle, it will launch this simulation step. Okay, so now the simulation step is launching. Let's go take a look at what's happening under the hood. We open up step functions. Here's our state machine. And we can see we have one active state machine. Let's go ahead and open it up. This current state machine, what's kind of neat with the visual workflow and step functions is you can actually see what's the current state of this process. So it looks like we've kicked off our batch simulations, and then we've entered this loop where basically we're checking the status every 30 seconds to see if the simulation is completed. In step functions, you can actually go see every single state change and the inputs and the outputs of that state change. So it's going to take a little while for these simulations to complete. While that's going through, let's go and actually see the simulations as they're running. Job batches. Okay, so here's our current job batch. Both of these simulations are preparing. If we open them up, let's open up each one. What we can see is this particular simulation application, if we go look at the tags, is the multi-nav bookstore, whereas this simulation application is the quick nav bookstore. So here it is up and running. Let's go ahead and open Gazebo. Okay, so here's our simulation. If we zoom in, we can probably find our little turtle bot somewhere around here. There he is. Roaming around and going to different navigation goals. So once the simulation job has completed, which it looks like this particular test has successfully completed, it will go ahead and self-terminate, and it's in that stage right now. It will also return the status of our test, and so we'll see that this particular test has passed. Okay, so now that both of our tests are either complete, oh, looks like they just both completed. Let's go back to the step function state machine. We ran the send sim summary. Let's go to the end here. It looks like the execution succeeded, and so this means that we've completed this step function state machine. 2 simulations successfully passed tests. So if we go back to code pipeline, all right, so it looks like we've successfully completed this code integration. We've run 2 different simulation tests, and now that this is configured, whenever our developers create a new feature, they can easily take their feature branch, merge it into the integration branch, and on every code integration, we're going to run through this set of tests. And that completes this section of the console walkthrough.
Okay, so now that we've built this CI pipeline, you're probably wondering how much this is going to cost. So let's break down some of those costs. First, we have RoboMaker costs. And so if you're using the integrated development environment, there's a cost for running that underlying EC2 instance. However, as soon as you close down your IDE, after a few minutes, it's going to automatically stop that instance. Therefore, you're only paying for the time that that instance is up and that you're actually doing active development. But that cost would be, if you're using an M4 large, about 10 cents per hour and about 10 cents per gigabyte storage. For simulations, which was the core of what we covered today, it's 40 cents per simulation unit per hour. For fleet management, it's 16 cents per registered device in a fleet. For code pipeline, it's $1 per active pipeline. Code build is the penny per build minute. So let's say you have an average about 10 minutes per build. That'd be about 10 cents per build. It's not too bad. Lambda functions are built on a per millisecond rate, which is quite small. So the amount of Lambda execution that you'll have in this solution is very small. Wouldn't really show up on your bills. For step functions, it costs about 2.5 cents per 1,000 state transitions, and S3 is about 2.3 cents per gigabyte stored. So if we're going to break this down into how much this particular solution costs, let's take a scenario as an example. Let's say you had took you about 10 minutes to build your code. Let's say you had about 4 code integrations per day. Let's say you had about 8 test scenarios that you wanted to run after each code integration, and it took about 5 minutes per simulation in order to complete that scenario. And let's say your application consumed about 5 simulation units when it was, so 5 vCPUs while it was in active operation. In this case, your build time would be about 40 cents per day. Your pipeline would be about 3.3 cents per day. The state transitions, 0.08. Simulation charges, about $5 a day for that. If you calculate them all together, that's about 160 simulation units. And then you have these ancillary costs of S3, Lambda, CloudWatch, these services that come with the operation of your CI pipeline. So all of this would come out to about $6.30 per day, or the cost of a cup of Joe. So as you can see, it's not very expensive to build in continuous integration pipeline into your regular development processes. This can not only prevent bugs that are introduced down the line closer to when you push your code into production, or at worst when your code is in production. It can help reduce the number of bugs. It can also help your velocity improve because your team is able to integrate their code more effortlessly without having to go back and fix issues when you integrate code, or bugs that are introduced from team members that may not have been developing their code in a consistent fashion. So this approach can really help you improve your velocity as well as reduce the amount of bugs and focus on the features that your customers are asking for. So that's all I have for you today. Hope you enjoyed today's presentation. Again, all of the resources are available on our GitHub repository if you go to AWS Robotics. So that's github.com/AWS-robotics, and you can find both the launcher as well as the sample application to create a very similar solution to what we showed you today. Thanks for joining.